This is slide number 58 and I am your presenter Asloob Mudassar. Incoherent imaging system. Equation 1 was written for a narrow band polychromatic light, and the aim here is to convert it to a perfectly incoherent case, in which scenario the phasors at the object plane vary completely randomly or more accurately in a statistically independent fashion. Being phasors completely uncorrelated, the 2 points zeta1 eta1 and zeta2 eta2 must coincide, otherwise the average of the phasor products at these 2 points will be 0. Consider equation number 18, which we have modified for the incoherent case. You know that here we are taking the average of the product of the phasors at point 1 and the conjugate and the complex conjugate of the phasor at another point. So u of g at point zeta1 eta1 as a function of time multiplied by the complex conjugate of ug, which is at zeta2 eta2 and time. The average of this quantity is equal to beta times ig or at point zeta and eta multiplied by the delta of zeta 1 minus zeta 2 comma eta 1 minus eta 2. So you see for the incoherent case we have introduced the intensity over here, and the intensity only at one point. Ig stands for the geometric optics intensity, and you know that here on the left hand side we have ug, which stands for the phasor, which stands for the phasor, which stands for the field, which stands for the geometric optics field at points zeta 1 and eta 2 as a function of time, and similarly complex conjugate of the field at another point zeta 2 and eta 2 as a function of time. You see that on the right hand side we have delta of zeta 1 minus zeta 2 and eta 1 minus eta 2. You see that this delta function will exist only when zeta 1 is equal to zeta 2 and eta 1 is equal to eta 2. But you know that why, okay, if we set these one equal to, if we set zeta 1 equal to zeta 2 and eta 1 equal to eta 2, then you know that there is no need to write the delta functions. But you know that we shall later see that this delta function we have retained over here is important because it will simplify some integrals. Now beta is a real constant. Equation 18 will hold if the coherence area around a point in the object plane is smaller than the resolution cell size centered at the point in the object plane. So you see that here we are talking about two terms. One is the coherence area at the object point, and the other is the resolution cell size at the object point. So you see that resolution cell size is concerned with the image plane where you have the CCD pixels, or where you have placed a digital camera, and you know that the size of the pixel size of that digital camera when traced back through an optical system, and the image is considered of that pixel through the imaging system at the image plane, then you see that we shall get a resolution cell size at the object plane. And you know that the coherence area, we have already considered a coherence area in such a way. For example, if you have a point, if you have a point image at the image plane, and if you trace back that point image through the optical system and get an area at the object plane, then that area is called the coherence area. So we have a point source which is located at the image plane, traced back at the object plane, give you an area which will give you a coherence area. And if you have a pixel, of a digital imaging device at the image plane, then a single pixel traced back at the object plane will give you at the object plane the size of the resolution cell, which we call resolution cell size. So you see that here we are comparing the two things here, that is the coherence area around a point in the object plane is smaller than the resolution cell size centered at that object point in the object plane. From the theory of coherence, we know that the minimum dimensions of the coherence area is of the order of wavelength of light. For a perfectly incoherent illumination, it is reasonable to assume that the resolution cell size around any object point is greater than the coherence area at that point. Equation 12 can be modified as given below. So you see that here we are modifying the equation number 12, which we have already described, and here we are going and where we have labeled that equation, that is equation number 10, previously labeled as 12. Now we are relabeling that equation as equation number 19. And you know that in equation number 19 we have replaced these terms on the left hand side which were present in equation number 12, and now we have replaced the average of the complex conjugate of the multiplication of the two phasors. One is the phasor and the other is the complex conjugate of the phasor, replaced by in equation number 19 by the right hand side of equation number 18, that is by beta ig at point zeta 1 and eta 2 and the delta of zeta 1 minus zeta 2 and eta 1 minus eta 2, as you can see in equation number 19. Okay. So you see that here we have the two integrals. One is the integral on the zeta and eta 1 coordinates, the other integral on zeta 2 and eta 2 coordinates, and you will see that there are two kappas present. One is the kappa at the coordinates u minus zeta 1 and v minus eta 1, and there is another kappa conjugate at the coordinates u minus zeta 2 and v minus eta 2. And you know that here we have introduced the quantity from equation number 18, that is beta multiplied by ij at point zeta 1 and eta 2 multiplied by the delta of zeta 1 minus zeta 2 and eta 1 minus eta 2. You see that here we can solve the value of this delta Dirac delta function in order to solve one of the integrals. So we are setting here, for example, zeta 2 is equal to zeta 1 and eta 2 is equal to eta 1 in equation number 19. Then one of the integrals will disappear, and you see that we have the two kappa functions, and we can take the complex and we can take the the absolute square of the kappa function, because two kappas have the same coordinates. One is kappa, the other is complex conjugate of kappa, and at the same coordinates we have the absolute value, absolute square of that value, absolute square of the value of the kappa, which we have shown in equation number 20 as kappa of u minus zeta 1 and v minus eta 1, and you know that then we have ig at zeta 1 and eta 2. So you see that in the first row of equation number 20 we have all the parameters which are only zeta 1 and eta 1 dependent, because the integration of variables is also zeta 1 and eta 2. And you know that in equation number 20 we have written the symbolic form of equation of the first step in equation number 20. So the symbolic form in the second step of equation number 20 is that is the intensity at the image plane as a function of u and v, which is the u and v are, you know, that the plane at the image plane at any point of the image plane we call it as uv. So on the right hand side we have beta multiplied by ig at the coordinates u and v, that is the intensity of the geometric optics image at the coordinates u and v, convolved with the absolute square of the kappa at the coordinates u and v. So you see that this is a symbolic form of that one, and you know that here the absolute square of kappa is an amplitude point spread function, but if you take the absolute square of this quantity then it becomes an intensity point spread function, or intensity response impulse response. So let's see. That is, for an incoherent imaging system, the intensity is proportional to the convolution between the intensity due to geometric optics Ig as a function of u and v and the squared modulus of the amplitude PSF. The squared modulus of the amplitude PSF, that is absolute square of kappa as a function of u and v, may be regarded as the intensity PSF. We can thus state that an incoherent imaging system is linear in intensity, in the sense that Ig in equation number 1 has a power equal to 1, and if we convert kappa, absolute square of kappa, into intensity, then you know that intensity PSF will also have a power equal to 1. So Ig has power equal to 1, the kappa converted into intensity will also have a power equal to 1. So we can say that incoherent imaging system is linear in intensity. And remember that, or recall that the imaging system, that the coherent imaging system is linear in amplitude. Okay, So you see that now we are discussing the domain in which we have the coherent system or the incoherent system. That is, under what condition we can identify that our imaging system is behaving as a coherent system or incoherent system. So let's discuss the domains under which a system can be categorized as coherent or incoherent. We are borrowing the results from the theory of partial coherence with the help of the figure below. So look at this figure. With respect to object point, so you see that if you look from the object point, from the center of the object point at the source plane, the dimensions of the source, the angular dimensions of the source is theta s, and if you look at from the same point on the object plane at the center of the object, if you look from that point to the entrance people of the plane, then you know that the angular width of that of the entrance people will appear as theta p. So theta p is the full angle, you know, that we have shown. And similarly, if you look at from the same point on the object, if you look at the angular spectrum of the field, then you know that the angular spectrum width will have a dimension, will have an angular dimension equal to theta naught. So you see that the object we have in this figure, we have the object plane, we have the source plane, we have the entrance people plane, we have the angular spectrum plane, and we are measuring the dimensions of all these other planes except the object plane, that is, we are looking from the object plane, and you know that the width of the source plane and the entrance plane and the angular spectrum have been labeled in this diagram. Angular dimensions of the source, entrance people, and angular spectrum as seen from the object plane respectively are given by theta s, theta p, and theta naught. An imaging system will be categorized as coherent or incoherent according to the following two equations. For example, consider the first equation. You know that generally speaking, that when we are talking about the coherent system, the dimensions of our point source must be very small. If we have a point source, then you know that will form an ideal coherent system. But you know that here we have shown some angular width of the source. So let's see that what conditions should be applicable for a system to be coherent. It is given by equation number 21. For a coherent imaging system, theta p is much greater than theta s. So look back at this equation, that is the angular width of the entrance people is much greater than the angular width of the source point. And that is described in equation 21. So equation 21 guarantees that we are using a coherent imaging system. Now let's consider the incoherent system. In the incoherent system, of course, the source angular width should be greater than, or should be at least equal to, the width of the entrance people. So let's talk about equation number 20. For incoherent imaging system, theta s is greater than equal to theta p plus theta naught. So you see that the sum of these two angles, which is theta p and theta naught, should be less than or equal to the dimensions, the angular dimensions of the source as viewed from the center of the object point, because we are measuring all these angular separations, all these angular widths from the center of the object point. So equation number 2 has been explained for an incoherent imaging system. We may conclude on the basis of equation 1 that if the angular size of the entrance pupil is much greater than the angular size of the source, we are in the domain of coherent imaging. And if you look at equation number 22, we may say that we may conclude on the basis of equation number 22 that if the angular size of the entrance pupil is comparable or smaller than the size of the source, then we are in the domain of incoherent imaging. The two inequalities present two extreme cases, because these two extreme cases, for these two extreme cases, an imaging system will behave as a partially coherent system if we are existing in between the two cases. So these two conditions are the extreme cases. Extreme case for the coherent case, for the coherent imaging as given in equation number 21, and extreme case for the incoherent case as given in equation number 22. Between these two extreme cases, an imaging system will behave as a partially coherent imaging system. So next we discussed coherent imaging transfer function. So coherent imaging transfer function. You know that, let me recall that transfer function is actually the Fourier transform of the point spread function. So if you have you know that in coherent imaging system we consider amplitude point spread function, and if you take the Fourier spectrum of that amplitude point spread function, the quantity that you get will be called transfer function. And you know that the points when we talk about the point spread function, the point spread function is actually an image of a point source under an optical system, and the point spread function is associated with the image plane, whereas the transfer function is associated with the spectral plane or the Fourier plane. So when an object is illuminated by a coherent plane wave, the field after the object may be considered as if consisting of many plane waves of different magnitudes and phases traveling in different directions, and a biconvex lens at a distance f from the object plane will focus them at its back focal plane, giving the Fourier spectrum of the object plane. So you see that when a plane wave illuminates an object, normally what will happen due to diffraction after the object, the field will be split, the input field will be split into many plane waves of different amplitudes and different fields going and different phases going in different directions. And you know that if there is a lens at a distance f from the object, that lens will collect these different Fourier planes and then will focus them at a plane which we call the Fourier plane, and each plane wave will be focused at a single point on the Fourier plane. The field beyond the Fourier plane will diverge out, because at the Fourier plane all the plane waves diffracted at the object plane will be received by the lens, and that lens will focus them at the Fourier plane, and you know that after the focusing the light will diverge out. So here we are talking about the field beyond the Fourier plane will diverge out and turn into plane waves where they interfere and produce an image in the far field. So you see that after the Fourier plane, because the plane waves are being focused at the Fourier plane, and after the Fourier plane they will diverge out and will increase into spherical waves, and you know that these spherical waves will interfere in the far field. In the far field they will turn back into the plane waves, because of the definition of the far field, those waves which are generated as a spherically diverging wave front from the Fourier plane, they will diverge out there, they will expand in their dimensions, and their small portions which will behave as a plane waves at a very large distance or in the far field, they will interfere with each other and will form an image, and you know that image is called the image in the far field. If an identical lens, now you suppose that if you don't want to measure the field at a very large distance, but you just want to measure the far field within the laboratory scale, what you need to do is that you need to place an identical lens that generated the Fourier plane just after the Fourier plane at a distance f from the Fourier plane, and you know that after that lens will collect the spherical waves from the Fourier plane and will focus them and will convert them into plane waves, and these plane waves will interfere at the image plane and which is at the back focal plane of the second lens, and you know that the interference will yield the image. So here what I have stated, that if an identical lens of a focal length f is placed at a distance equal to its focal length after the Fourier plane, then the image will be formed in the near field at the back focal plane of the lens. So you see that here I am going to describe that one in the diagram. So look at this diagram. This is called 4F imaging system. 4F in the sense that we have four separations equal to f. So lens L1 is at the back focal plane of the object at a distance equal to f, or in other words you can say that the object plane is located at the front focal plane of lens f1 of lens 1. So there is a Fourier plane which is located at the back focal plane of lens L1. So there is a distance f between the Fourier plane and the lens L1, and you see that we have placed another lens L2, and the Fourier plane lens L2 is placed in such a way that the Fourier plane is located at the front focal plane of the lens L2. That's why the separation between the Fourier plane and the lens 2 is equal to f, and the image plane, you know, that is located at the back focal plane of lens 2, which is in the Fresnel region or in the near field, and you know that again the distance between lens 2 and the image plane is equal to f. So you see that that's why there are 4 f systems. That's why it is the 4 f systems, because f is the separation between the consecutive components. And you know that here the incident plane wave is incident normally at the object plane. This incident plane wave, when hitting the object plane, that at the object plane it will be converted into many plane waves due to diffraction at the object plane, consisting of plane waves going in different directions, having different amplitudes, having different phases depending upon the thickness of the object. And you know that this lens L1 will collect some of these plane waves, and you know that this lens L1 will focus those plane waves at the Fourier transform plane. And you know that at the Fourier transform plane we shall get different spots, different light spots, because each plane wave will be focused at a single point, sharply focused points on the Fourier plane. So Fourier plane may contains many plane waves depending upon how many plane waves will incident on the lens L1. So if a lens L1, for example, collects 10 plane waves, then you know that the Fourier plane will consist of 10 light sources, that is 10 Fourier frequencies. And after the focusing at the Fourier plane, these point sources at the Fourier plane will diverge out, will act as sources for the spherical waves outgoing in the z direction. So these spherical waves will hit the lens L2. The lens L2 will convert them into plane waves. So you see that the same number of plane waves equal to the number of spherically diverging waves hitting the plane waves will be traveling towards the right, and at the image plane all these plane waves will interfere with each other and will form an image. So let's read. A 4F imaging system is shown. In the absence of lens 2, the image plane will be located in the far field. So you see that if lens 2 is not present, then this image plane has to be located at infinity, at a very large distance, so that the spherical waves coming out from the plane waves will become some portion of that one will behave as plane waves at a very large distance, so they will interfere and form an image. So a 4F imaging system is shown. In the absence of lens 2, the image plane will be located in the far field. Object is located at the front focal plane of lens L1. Object is located at the front focal plane of lens L1, and the image plane is at the back focal plane of lens L2. In between the two lenses, the Fourier plane is located. The field at the image plane is a linear mapping of the field at the object plane. Here we limit ourselves to a diffraction limited space invariant coherent imaging system for which we can write. So you see that we are now writing in equation number 23 the field at the image plane denoted by ui as a function of u and v on the left hand side, and the double integral includes kappa as a function of u minus zeta v minus eta, and uj, which is the geometric optics field at the coordinates zeta and eta, and you know that integration is with respect to d zeta and d eta. So you see that we have written kappa as u minus zeta and v minus eta. It means that the difference shows that we have written this kappa for an invariant system. And you know that here we are also talking about the diffraction limited space invariant system, so that only the diffraction will deteriorate the quality of the image, of the amplitude image. There are no other defects present in a lens. So you see that we have only this one, and the kappa, you know that the difference between the coordinates in the kappa indicate that we are talking about an invariant system. And the diffraction limited system also means that we have considered only an isoplanic region of the lenses. Isoplanic region, or in other ways you can say that we have considered the small regions around the center, around the z-axis or around the optic axis of these lenses. That is, we are dealing in the paraxial region of these lenses. The object is located at the zeta eta plane, and the image coordinates are the uv plane, and the Fourier coordinates are the fx and fy plane. So we have given the coordinates at these three planes also. Now you see that we are taking the Fourier, we have written in equation number 24 the symbolic formation of equation number 23. If you recognize on the right hand side the integrals, these integrals are just the convolution integrals. So the convolution between UG and kappa, or the convolution between kappa and UG, they are identical with respect to each other, because the convolution are commutative. So you can write in equation number 24 that ui as a function of u and v is equal to kappa as a function of u and v convolved with ug as a function of u and v. You see that here we have written the coordinate of ug as u comma v. Whether you write at the object plane or whether you write at the image plane, both have to be the same, because ug at the object plane is the same as ug at the image plane, because this is a geometric optics image. Okay, now you see that let's take the Fourier transform of equation number 24. We have used a Fourier operator on the left hand side of ui, and similarly we have used the Fourier operator on the right hand side of equation number 24. So we are representing ui, the Fourier transform of ui, as gi. We are labeling it, or we are naming it that the Fourier of ui is gi, and but you know that the coordinates are fx, fy. And similarly, when we take the Fourier transform of these two quantities which are convolving each other, then it will be equal to the Fourier transform of first quantity, that is kappa, and the Fourier transform of the multiplied by the Fourier transform of the second quantity, which is ug. So the Fourier transform of ug has been labeled as capital G with the subscript of small g, capital Gg, as a function of fx, fy, and the Fourier transform of kappa, which is written in small k, has been written as capital K, and C stands that it is for the coherent imaging system. And you know that again the coordinates are fx and fy. So equation number 25 is a Fourier version of equation number 24. That is, we have taken the Fourier transform of that one. And you may recall that these quantities are actually the Fourier spectrum of these you may say Fourier transform, or more accurately the Fourier spectrum of the quantities shown in equation number 24. So let's describe these quantities individually. For example, gi, which is the Fourier transform of ui, has been shown, you know, that through the Fourier integrals. So the double integral of ui as a function of u and v, and you know that the rest of the parameters are associated with the Fourier transform. Here we have e to the power minus iota 2 pi. Within the parentheses we have fx into u plus fy into v, and you know that we have du and dv. So this is equation number 26. And similarly we can write for equation number 27 and for equation number 28. So Gg, you know that as we have described this, it is the Fourier transform of Ug, and you know that integral contains Ug and rest of the parameters is the Fourier parameters. So capital Gg on the left hand side is equal to the Fourier transform of Ug on the right hand side. And you know that you can notice the variables that on the left hand side we are using the variables at the Fourier spectrum, which is fx, fy, and on the right hand side we are using the Fourier the parameters at the image plane. So similarly we have kx as a function of fx, fy, and within the integral on the right hand side we have kappa as a function of u and v, and the rest of the quantities are the definitions of the Fourier transform. So we have described equation number 26, 27 and 28, giving the Fourier descriptions of the quantities we have shown in equation number 25. Kappa c as a function of fx, fy is the Fourier transform of the amplitude PSF, or the Fourier transform of the amplitude impulse response of a diffraction limited space invariant coherent imaging system, and is termed as the transfer function of the coherent imaging system. So kappa c is the transfer function of the coherent imaging system. C stands for the coherent. The energy spectrum, which is the absolute square of a kappa c as a function of fx, fy, the absolute square of a kappa c can be observed by inserting a piece of a flat paper at the Fourier plane. So kappa is the absolute square of kappa is actually the energy spectrum. Put a piece of paper at the Fourier plane and you will observe the energy spectrum there. And you know that this kappa, actually sorry, this is not kappa, but this is the Fourier spectrum. This is the what we call it. This is termed as the transfer function. So kappa c is the transfer function. So this is the absolute square of transfer function, which we call it as the energy spectrum. So put a piece of a paper in the Fourier plane and you will observe the transfer function, that is you will observe the energy spectrum of the imaging system. So next, in equation number 29 we relate kappa as a function of u and v with the exit people of the imaging system through the equation, that is kappa is equal to a over lambda zi multiplied by the Fourier transform or the Fourier spectrum of the exit people of the function, So a over lambda zi, and you know that the Fourier transform of the exit people over here in this case is p of xy. So p of x comma y, you may call it entrance people, you may call it exit people, but you know that we have discussed that we shall be using the exit people as the people of the imaging system. So here the Fourier transform of the exit people is equal to the double integral, and we have used here p of x comma y, and the rest of the quantities are related with the Fourier spectrum, which is e to the power minus iota 2 pi over actually u over lambda zi is actually fx, which we have given at which we have converted into space coordinate by using the value u over lambda zi, and similarly v over lambda zi in equation number 29 is fy, and which we have converted it into the space variables v over lambda zi. So we have taken lambda zi common, so we have the exponential e to the power minus iota 2 pi over lambda zi, and within the bracket we have ux plus vy, and the integration is with respect to dx and dy, because our pupil function depends upon x and y coordinates. So x and y coordinates defined at the lens plane, at the lens 1 plane, because if we assume that our system consists of a single lens, then of course the entrance people and the exit people and the physical aperture, all the three apertures will be identical to each other. So xy are the coordinates defined at the lens 1 plane, and p of xy is the pupil function of the lens 1, and then zi is the distance of the image plane from the z1. Kappa of uv is the image of a point source. So remember that kappa is the image of a point source located at the object plane. A is the amplitude of a spherically diverging wavefront incident on the lens 1 and originating from a point amplitude from a unit amplitude point source located at the object plane at a distance greater than f. You see that if you form a real image through a single lens, then of course the object should exist at a distance greater than f, and you know that we are considering that the object contains a single point source through which a spherically diverging wavefront is coming out and hitting the lens L1, and the lens L1 of course will form an image of that one at a distance zi behind the lens. So in equation number 30, what we have to do is that the next step is to find the relationship between the coherent transfer function, that is the capital Kc as a function of fx comma y, and the pupil function of the imaging system through imaging system lens L1, and you know that we have the transfer function, we have the Fourier transform of kappa function. The Fourier transform of the kappa function as given in equation number 29 is related with the pupil function p of xy. So you see that substituting the value of a kappa in equation number 30, you can find out the relationship between the transfer function between the coherent transfer function of the imaging system and the pupil function of the imaging system. So let's do that. That is replace kappa in equation number 30 by its value from equation number 29, and this is what we have done in equation number 31. So you see that this Fourier operator will go inside the integral, because this Fourier operator is a function of u and v. So it will operate only on u and v, that is it will operate on the exponential part, because the exponential part contains u and v. So let's send kappa inside the integral. Let's send operator Fourier operator inside the integral, as we have shown in the first row of equation number 32, that the operator is operating only on the exponential part, and you know that the Fourier transform of this exponential part we have written directly. It is equal to del delta of fx minus half alpha comma fy minus half beta dx and dy. This beta is not the same as we have used previously in some intensity expression, but this beta is, you know, that a different parameter which we have defined in below the equation number 32. So let's look at equation number 32. In the second row, that we have the double integral containing p of xy and of course the delta of fx minus half times alpha comma fy minus half times of beta. And you know that since this integral is with respect to dx and dy, we would like to convert fx and fy, these two Fourier frequencies, in terms of the space variables, so that we can represent it in x and y variables. And you know that the formula is alpha is equal to minus 2x over lambda zi and beta is equal to minus 2y over lambda zi. These are actually two parameters, alpha and beta, which appear in the definition of the Fourier transform of the exponential given in part number 1 of equation number 32. So you see that we have now used the values of x and y, that is alpha and beta, after in equation number 33. So you see that rearranging these equations through simple calculus, you can see that delta of xy now contains lambda zi fx plus x comma lambda zi fy plus y and dx and dy. And you know that here we have also used the value of fx and fy, because fx is equal to x over lambda zi and we have retained the value of fx and fy, and just we have substituted the value of alpha and beta there. So you see that this is the integral. Now you see that in order to evaluate this integral, what we need to do is that we need to replace the value, we need to replace the arguments in the function p that has x and y by the arguments of the delta functions. So you see that this delta function will be 0. That is, the delta function will contain two coordinates, that is, the arguments of the delta function will be 0 and 0 only when x is equal to minus lambda zi fx and y is equal to minus lambda zi fy. To set the arguments of the delta function equal to 0, we have the values of x and y which we have replaced in the people function. So now the people function, the x and y has been replaced by lambda zi fx comma lambda zi fy, and the integral, you know, that has vanished because we have used the properties of the delta function there. So you know that since people function is a symmetric function in the people function is a symmetric function at the length plane, we can replace is a symmetric and also an even function. So you see that using the definition of the property of the even function, we can write equation number 33 as that is the transfer function on the left hand side kc as a function of fx comma fy is equal to a lambda zi multiplying to the people function which has the arguments as lambda zi fx comma lambda zi fy. So this equation number 33 has been described. Now you can see that we have found a direct relationship between the transfer function on the left hand side and the pupil function of the lens on the right hand side, or the pupil function of the exit pupil. In equation number 33, in the last step, we have omitted the negative signs because p is an even function. The lens pupil p of xy is defined below, where r0 is the radius of the pupil. So you see that this pupil function is equal to 1 when x square plus y square, the square root of this quantity is less than or equal to r0. So in this radius, the pupil function will behave as a transparent or the clear aperture, and you know that when we violate the condition of the radius r0, then you know that we have the 0, that is the pupil function is contained in a opaque region of radius equal to r0, which is clear as given in equation number 34. So you see that we can modify the definition, or we can adopt the definition given in equation number 34 for the pupil function at the end, given in equation number 33 at the end. Okay, so we have converted that one as shown in equation number 35, that p of lambda zi fx comma lambda zi fy is equal to 1 when the square root of lambda zi fx square plus lambda zi fy square is less than or equal to r0. So this will behave as a clear aperture for this radius r0 again, but you know that here we have given the conditions for in terms of other parameters, and you know that 0 otherwise. So we have also converted, you see that we have solved the square root of the above equation, and we have written it as the second definition, that p of lambda z I fx comma lambda z I fy is equal to 1 when the square root of when the square root of fx square plus fy square is less than or equal to r0 over lambda zi, and 0 otherwise as given in the last step of equation number 35. Now the transfer function kc as a function of fx comma y from equation number 33 takes the following form. So you see that in equation number 38 we have defined kc, and now we are writing it in more specific form, giving some more constraints. So kc as a function of fx comma y, which is the transfer function of the coherent imaging system, is equal to a into lambda zi multiplied by the pupil function containing arguments as lambda zi I fxy comma lambda zi I fy, and you know that this is contained within the curly bracket, that this transfer function is equal to a lambda zi if fx square plus fy square, the square root of this quantity is less than or equal to r0 over lambda zi and 0 otherwise. So you see that now we have, since this capital C, you know, that is defined at the Fourier plane, you can see that it is given as a function of fx and comma fy. It means that we are talking about the Fourier plane, and we have also limitizing the size of the Fourier plane by giving that the square root of fx square plus fy square is less than or equal to r0 over lambda zi. So over Fourier plane will in the Fourier plane our transfer function will exist in this region, that is less than or equal to r0 over lambda zi. Now if we compare equation number 34 with equation number 36, this is equation number 36a and this is equation number 34. So if we compare, you see that here we are using the radius r0 in equation number 34, and in equation number 36 we are using the radius r0 over lambda zi in the Fourier plane. So comparison of equation number 34 with equation number 36 reveals that if r0 is the radius of the lens pupil function, then r0 over lambda zi will be the radius of the clear aperture at the Fourier plane through which the Fourier frequencies will pass and outside which the Fourier frequencies will be stopped completely. The presence of a lambda zi in equation number 36. Notice that the presence of a lambda zi in equation number 36a. So the presence of a lambda zi in equation number 36a indicates that the Fourier frequencies that will pass through the aperture at the Fourier plane will be multiplied by this factor, which means that the amplitude of each Fourier frequencies within the aperture defined by equation number 36 will be modified by the factor a lambda zi, where the phases of these frequencies will remain unaffected. You see that in equation number 36 there are no phase factors, so the transfer function will not change the phase of the frequencies which are passing through the Fourier plane and restricted by this capital Kc. So that is, the coherent transfer function does not affect the phases of the Fourier frequencies passing through the aperture defined by equation number 36, but it does affect the amplitude of the by the factor a lambda zi. The factor a lambda zi appears implicitly in the Fourier transform of input object fields and can be ignored in equation number 36b, which reduces to the following form. So you see that here in equation number 36 you see that we have a lambda zi which multiplies to each Fourier frequency and changes the magnitude of each Fourier frequency. But you see that if we omit this one and if we set this one equal to unity, then you know that the physics will not change and the image quality will not be affected by this factor if we set it equal to 0. So we have set that one equal to 0. So we have redefined capital Kc as a function of fx comma y, that is the definition of the transfer function, in terms of the pupil function as a function of lambda zi fx comma lambda zi fy is equal to 1 when the square root of fx square plus fy square is less than or equal to r0 over lambda zi and 0 otherwise. This is the more defined definition of equation 36a, which we have given in 36b. The amplitude transfer function is thus equal to the scaled pupil function defined at the length plane with the scaling factor equal to lambda zi. Length pupil function p of xy and the coherent amplitude transfer function as the scaled length pupil function are shown. So you see that in this figure you will see that we have shown an input object plane, we have shown the thin convex lens and the Fourier plane. The input plane is located at the zeta eta plane, the lens is located at the xy plane, and the Fourier plane is located at the fx fy plane. And you know that you can see that we have labeled there as a capital KC as a function of fx comma fy because it is located in the clear aperture. Within the clear aperture, capital KC is unity within that region and 0 outside. So you see that we have defined a pupil function p of xy at the lens plane. So the lens aperture is actually the pupil function of the lens or the pupil function of the system if it is consisting of a single lens. And you know that in the Fourier plane we have also shown a transfer function which is the capital KC as a function of fx comma yy. So the clear aperture at the Fourier plane is actually a representation of the transfer function of the system, because only those frequencies which lie within the clear aperture will pass through the system. The rest of them will be blocked, which are lying in the black region. In deriving equation number 36, we used the point spread function from equation 4, which did not contain quadratic phase factor that appears because of the planar object. Okay, we have already discussed the methods of removing the quadratic phase factors related to the object plane and to the image plane earlier. Spherically converging wavefront are useful to eliminate the object related quadratic phase factors. And you know that this object has the coordinate zeta and eta, and the object related quadratic phase factors will contain zeta square and eta square terms. So that terms can be completely eliminated, as we have seen before, that if the object is illuminated with a spherically converging wavefront. In many optical elements, if many optical elements form an imaging system as an black box, and if the Fourier transform of the object under spherically converging wavefront appears at the entrance pupil of the system, then it would also appear at the exit pupil, as both pupils are images of each other. So that is, you know that this definition is quite evident, that if at the entrance pupil the wave incident is spherically converging, then you know that the same wavefront will also appear at the exit pupil, because both are images of each other. The coherent amplitude transfer function is also regarded as the top hat function because of its appearance as shown. So you see that we have shown the transfer function Kc as a function of fx and fy. It has a maximum value of amplitude equal to 1, which we have labeled there, and you know that there are two Fourier frequencies, fx and fy. And you know that in this clear region the Fourier frequencies can pass, and in the opaque region, which we have shown as black, the Fourier frequencies will be completely stopped. The coherent amplitude transfer function is also regarded as the top hat function because of its appearance as shown. The radius of the clear aperture is R0 over lambda zi, where R0 is the radius of the lens pupil function. The cutoff frequency at the Fourier plane is imposed by this amplitude transfer function is f0 is equal to R over lambda zi. So from the above definition of the Fourier transform that we have given over here, we can see that the cutoff frequency of this transfer function, which we label as f0, is equal to R0 over lambda zi. For completeness, let's now consider the pupil function of the lens as a rectangular aperture with width equal to 2wxi along the x-axis and 2wy along the y-axis. Then the pupil function can be defined as the multiplication of the product of multiplication of two rect functions, that is the rect of x over 2wx and rect of y over 2wy, as in equation number 37. So this is a rectangular pupil function now at the lens. So let's see. Let's now evaluate the shape of the Fourier transfer function. The transfer function is given by equation number 36. Takes the following form. So transfer function and the pupil function are related by the equation given in the first step. So Kc as a function of fx, fy is equal to p of lambda zi fx, lambda zi fy. So you know that now we are going to use the value of p because we have defined p over here. So using the value of p as these arguments, we are writing the rect as lambda zi fx over 2wx and other rect as lambda zi fy over 2wy. So now we can adjust the parameters. We can keep fx and fy in the two rects respectively in the numerator, the other terms in the denominator. So the other terms in the denominator can be labeled as the cutoff frequencies, that is 2fx and 2fy respectively, as in the last step of equation number 38, where f0x, that is the cutoff frequency along the x direction, is wx over lambda zi, and fy is the cutoff frequency along the y axis, which is wy over lambda zi. The transfer function being symmetric about the zeroth order frequency along the two axes, that is along the fx axis it is symmetric, along the fy axis it is symmetric. The rectangular transfer function has cutoff frequencies from minus f0x to plus f0x along the fx axis and minus f0y to plus f0y along the fy axis. So the mod of these values, that is the mod of f0x and mod of f0y, are the cutoff frequencies along the fx and fy directions respectively. So you see that here we have shown the shape of the rectangular aperture, a rectangular transfer function due to the rectangular pupil function we have used. So look at that the magnitude of this, that the height of this is 1. So we have shown the two axes, fx axis and fy axis. You can see that the width along one of the direction is 2f0y, which is 2wy over lambda zi along the fy frequency, and along the fx frequency the width of this rectangular transfer function is 2f0x. 2f0x is equal to 2wx over lambda zi. Equation 36 was derived treating p of xy as the pupil function of a single lens, but if p of xy is also assumed to be the exit pupil of a system consisting of many optical elements, the theory presented and equation number 36 derived would remain completely valid. So you see that if we have considered p, you know that in the previous discussion we are assuming that p, that is the pupil function, is the pupil function of a single lens, and the imaging system is consisting of a single lens. But you know that if imaging system consisting of a black box containing many optical systems, then you know that in that case the pupil function will takes the terminology of the exit pupil, that is the exit pupil of the system will act as the pupil function. The rest of the derivations and the theory will be the same, and the equations will also be applicable and will also be valid. For both circular and rectangular apertures, the corresponding transfer function have same values within the pass band, which is unity, and abruptly go to 0 in the region beyond the cutoff frequency. So you see that you can see that within the cutoff frequency, the amplitude of the transfer function is equal to unity, and in the black region it becomes immediately equal to 0 or abruptly equal to 0, where the Fourier frequency will not pass and will be cut off immediately. In the theory presented, we have assumed aberration-free, diffraction-limited system. The picture will be entirely different if aberrations are included in the system. This case will be presented later on. In this case, the transfer function capital Kc as a function of fx, fy is a real and non-negative quantity when there are no aberrations. So this is the end of slide number 58.